We are now on to Thursday's lesson, which deals with making inferences. Just want to remind you guys that Imagine Math competition is happening, so make sure you're working on that. Also, make sure you're working on these lessons in chronological order. So if you haven't done Tuesday or Wednesday yet, you need to go back and do Tuesday and then Wednesday before this video. And office hour reminders are in the bottom right as well. So, the students in Mr. Coffee's class cast their votes in the school-wide vote for which color to paint the cafeteria walls. Based on the data, what might you conclude about how the rest of the school will vote? You can see the title here. It is Inferences. Today we're going to work on making inferences, and hopefully inference isn't a word you've heard before, or you haven't heard maybe inferences, but you've heard the word infer. Now, an inference or to infer is to make a prediction. So maybe you've heard it in ELA class and you needed to infer what the author is saying. We are going to use inferences and inferring similarly in math class. But how we're going to do that is we're going to use data, and based on that data, make an inference or a prediction. So the word inference is like a prediction, but it's an informed prediction. It's not random. It's based on data. So let's look at this. Some of the inferences I can make off the bat just by looking at it very quickly. It doesn't look like yellow is very popular, right? I see 3 yellows. It looks like blue is very popular. Red seems to be fairly popular too. So it seems like it's a competition really between blue and red, and the other colors, particularly yellow and green, not being the most, and orange, not being the most popular. So that's just like a baseline inference. But I can dive deeper into what's happening here with the votes in Mr. Coffee's class. So the first thing I'm going to do is I'm actually going to count the number of red. So we got 1, 2, 3, 4, 5, 6, 7. So we had 7 people here who would want the cafeteria walls to be painted red. I'm going to look at blue next. And I'm going to color coordinate these just for organization. We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So blue seems to be the most popular. I'm going to count that a second time to make sure no errors are made. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Cool. Next one, let's look at yellow. Yellow only had 3. Let's look at orange. And orange has 1, 2, 3, 4. And then green has 1, 2, 3, 4. All right. Now, in total, let's see how many votes were cast. We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 30. So this should add to 30, and I'm going to double check this and make sure it does. 7 plus 12 is 19, plus another 3, plus another 4, plus another 4. It does add to 30. So this is a sample. It is not a population because remember, we're doing a school-wide vote. So that means every student in the school. We are taking this small sample, which is Mr. Coffee's class, which is probably a good representative sample generally. It's at least a good representative sample for maybe middle school students. Maybe it doesn't maybe scale down to how a kindergartner or pre-K or first grade student may vote, but it's a decent representative sample. And based on this, right, let's say we're talking about blue. 12 out of the 30 votes were blue. We could use this sample in order to make an inference, let's say, about how many people would vote for blue if there are 300 total students, right? By multiplying by 10, and you would be able to infer, based on the data, the sample data here, that if there were 300 total kids, about 120 would prefer painting the cafeteria blue. Based on the survey we have here, it looks like blue is going to be in the lead. But once again, a sample is just a small representation of the whole. If you actually ask the entire population, it may look a little bit different. But as long as the sample is representative and matches your population, you're going to get a pretty high level of accuracy. Now, let's move to some examples. I want you guys to make sure you are writing these down. And I'm going to move these up just so we're clear with the expectations. Boom. All right, so make sure you're writing these down. You can read through it as always and paraphrase it. Jayla surveys 3 different samples of 20 students, selected randomly from a population of 492 students in the 7th grade about their choice for class president. So, first of all, the reason she did the random sampling, 492 people is a lot of people. For Jayla to go one by one and ask every single student what they're voting, it's not the best strategy. It's too time consuming. It doesn't really make sense. Now, it would give you the most accurate data, but like sometimes you just can't do that. In each sample, Elijah receives the least amount of votes. Jayla infers that Elijah will not win the election. Is her inference valid? Explain. All right. We need to make sure we understand when an inference can be valid. And an inference can only be valid if the data you collected was done with validity. And what does that mean? That means the data you collected represents random representative sample. That's what we went over on Wednesday or yesterday or the previous lesson, depending on when you're doing it. But you can't really make an educated inference if the sample you have is not a random representative sample of the population. What Jayla did here is she did 3 different, which is great, 3 different samples. So she didn't just do one. She did 3 different ones of 20 students selected randomly. So if Elijah received the least amount of votes in all 3 of those, and all 3 of those were conducted randomly, which is always a plus, and she did it 3 times, the inference Jayla made of Elijah not winning the election is valid. So, let me make it smaller, be clear, and put this in words in your notebook. Because Jayla used simple random sampling, her sample sizes are likely to be representative of the population. Therefore, she can indeed infer that Elijah will lose the election since he received the least number of votes in all 3 samples. Okay? This question is getting you to think critically about, was the data collection method sound? Right? Is it representative? Is it random? If Jayla just asked 10 of her closest friends 3 times, we can't make any inference about that because it's not representative of the school. Okay? It needs to be random, it needs to be representative, meaning it needs to be diverse, and it needs to match the population of the school. All right, now example number 2, we're actually going to make numerical inferences. So Kamari is writing a report on cell phone usage. He collects data from a random, so that's good start, right? Good data. It's a random sample of 7th graders in his school and finds that 16 out of 20 7th graders have cell phones. If there are 290 7th graders in his school, estimate the number of 7th graders that have cell phones. So Kamari did a random sample, which is great, and his sample matches population. He is just doing a random sample of 7th graders because the population we're looking for is just the 297th graders. If the population we were talking about is how many kids in the entire school, Kamari's sample wouldn't be very good here because he only had 1 grade level, right? Your sample should match your population. All right, now let's set this up. And let me set it up like a proportion. So we got 16 out of 20 in his random sample had cell phones. Now, what we're essentially doing here is we are scaling this up to figure out, all right, how many had cell phones out of the total 290. We're making an inference or a prediction based on our small sample. Now, you can cross multiply or divide, or you can use scale factor. It does not matter. Anyways, here, x ends up being 232. Okay, so we're going to write this in a complete sentence because it is a word problem. So if, make that smaller. My apologies. Boom, boom. If there are 297th graders, the number of students who have cell phones would be approximately 232. I'm always going to say approximately because remember what we're doing. We're taking a small group and we're using it to make a prediction about the entire group. So you can't say there would for sure be 232. That is our estimation based on our sample. Now, another thing you could do here is you could divide 16 by 20, basically convert this into a decimal, and you would get, struggling with the size here, you would get 8/10, and then you can take that and multiply it by 290, because basically 8/10 of students have cell phones based on our sample, and that also gets 232. I think probably most of us are comfortable with either the scale factor or the cross multiplication and division, but there is multiple methods in order to solve this. All right, we're going to look at one more here, and before I mess up, I'm going to fix my font size now so I don't make another mistake. All right, the three fishermen, so we have three samples, similar to Jayla doing three samples, collected data on three different samples of 200 fish out of a catch of 1,000 fish. Shamar says that about 500 bluegill are caught for every 1,000 fish. Is this a valid inference? Explain. So we need to determine based on the numbers, does this prediction make any sense? Yes or no? Well, the first thing I'm looking at is I'm going to find the total here. And the total here ends up being 308. Now, why did I do that? Well, because it's going to provide me with some useful information. Because what this is telling me is that is telling me three fishermen collected data on three separate samples of 200 fish. Out of the 200, 400, 600, right? Because they're taking samples of 200 fish. So we had 308 bluegill fish out of the 600 total catches. Once again, that 600 is coming from the fact each sample was 200 total. 200 three times gets 300. Now, Shamar is saying there will be 500 caught for every 1,000. So we need to scale this up instead of 600 total to 1,000. Now, we can cross multiply and divide. We can divide 308 by 600 and then multiply. But what we're going to get here, x is approximately equal to 513.3. It is 513 and a third. I rounded it. So the question is this a valid inference? Yes. Shamar's inference. Sorry, make sure you're writing this down. I need to move those up next time, but make sure you're writing down. Shamar's inference is valid because 500 is fairly close to our mathematical calculation of 513.3. All right? So for Shamar to say it's going to be about 500, 513 is very close. And this is, I want to reiterate, this is data informed. You're collecting data to make an inference. These aren't random inferences. We're not just coming out with predictions nowhere, right? From nowhere. They need to be backed by data and numbers. This was backed by data and numbers, okay? This was backed by actual evidence, data and numbers, and so was this. So when you guys are making inferences, they're well-informed predictions based on data. And for this, when you have enough information, you are using proportional reasoning, like we did for this example, and I kind of hit on this example in order to make as accurate predictions as possible. All right, what you guys are going to go do now is you're going to take care of Thursday's quizzes. And then at that point, you should be done with 3 for the week. And the only thing left is a Friday Google Doc that honestly is not too long. It's only 3 questions. So you're almost there. You're almost done for the week. Reach out with questions if you have them.